Next, we are going to introduce another language model to represent text, which is a variation of bag-of-words model. Call them frequency inverse document frequency, or short for TF-IDF. This is a technique to quantify words in a set of documents. We generally compute a score for each word to signify its importance in the document or corpus. This method is a widely used technique in information retrieval and text mining. This is the principle behind TD-IDF. It works by increasing proportionally to the number of times a word appears in a document, but is offset by the number of documents that contain the word. Let's say, if I give you a sentence, for example, this building is so tall. It's easy for us to understand the sentence as we know the semantics of the words and the sentence. But how can any program interpret this sentence? It is easier for any programming language to understand textual data in the form of numerical value. So, for this reason, we need to vectorize all of the text so that it is better represented. There are some terminology in the TF-IDF models. Firstly, we have term frequency. Term frequency measures the frequency of a word in a document. This highly depends on the length of the document and the generality of the word. For example, a very common word such as worse can appear multiple times in a document. But if we take two documents with 100 words and 10,000 words respectively, there is a high probability that the common word worse is present more in the 10,000 worded document. But we cannot say that the longer document is more important than the shorter document. For this exact reason, we perform normalization on the frequency value. We divide the frequency with the total number of words in the documents. We call that we need to finally vectorize the documents. When we plan to vectorize documents, we cannot just consider the words that are present in that particular document. If we do that, then the vector length will be different for both the documents, and it will not be feasible to compute the similarity. So what we do is that we vectorize the document on the vocabularies. Vocabulary is the list of all possible words in the corpus. We need the word count of all the vocabulary words and the length of the document to compute term frequency. In case the term doesn't exist in a particular document, that particular term frequency value will be 0 for that particular document. In an extreme case, if all the words in the document are the same, then term frequency will be 1. The final value of the normalized term frequency value will always be in the range of 0 to 1. You may ask a question here. If we already compute the term frequency, and if this produces a vectorized form of the document, why not just use term frequency to find the relevance between documents? Let me explain. Words which are most common, such as is, are, will have very high values, giving those words very high importance. But using these words to compute the relevance produce bad results. These kinds of common words are called stop words. Although we will remove the stop words later in the pre-processing step, finding the presence of the word across the document and somehow reduce their weightage is more ideal. That is why we will also compute inverse document frequency. Document frequency measures the importance of document in a whole set of the corpus. This is very similar to term frequency, but the only difference is that term frequency is the frequency counter for a term T in document D, whereas document frequency is the count of occurrences of term T in the document set N. In another word, document frequency is the number of documents in which the word is present. We consider one occurrence if the term is present in the document at least once. We do not need to know the number of times the term is present. To keep this also in a range, we normalize by dividing the total number of documents N. Our main goal is to know the informativeness of a term, and document frequency is the exact inverse of it. That is why we inverse the DF. Inverse document frequency is to inverse the document frequency which measures the informativeness of term T. When we calculate IDF, it will be very low for the most occurring words such as stop words. This finally gives what we want, a relative weightage. Now, there are a few other problems with the inverse document frequency. When we have a large corpus size, say N equals 10,000, the inverse document frequency value explodes. So, to dampen the effect, we take the logarithmic of inverse document frequency. Finally, by taking a multiplicative value of term frequency and inverse document frequency, we get the TF-IDF score. There are many different variations of TF-IDF, but for now, let us concentrate on this basic version. The TF-IDF vector will increase with the number of occurrences within a document, and it will also increase with the rarity of the term in the document collection. Once you've transformed words into numbers in a way that machine learning algorithm can understand, the TF-IDF score can be fed to algorithms such as naive Bayes or support vector machine, greatly improving the result of more basic methods like word count. TF-IDF enable us to give a way to associate each word in the document with a number that represents how relevant each word is in that document. Then, documents with similar relevant words will have similar vectors, which is what we are looking for in the machine learning algorithms. TF-IDF model has many applications. For example, information retrieval. TF-IDF was invented for document search and can be used to deliver results that are most relevant to what you are searching for. Imagine you have a search engine and somebody looks for LeBron. The result will be displayed in order of relevance. That's to say the most relevant sports articles will be ranked higher because TF-IDF gives the word LeBron a higher score. It's likely that every search engine you have ever encountered using TF-IDF scores in its algorithms. TF-IDF is also useful for extracting keywords from text. The higher scoring words of a document are the most relevant to that document, and therefore they can be considered keywords for that document. And this is pretty straightforward. It is useful to understand how TF-IDF works so that you can gain a better understanding of how machine learning algorithm functions. While machine learning algorithms traditionally work better with numbers, TF-IDF algorithms help them decipher words by allocating them a numerical value or vector. This has been revolutionary for machine learning, especially in fields related to NLP such as text analysis. In this session, I'm going to introduce the word embedding model, which is another method to represent words in the form of vectors. Word embedding is a term used in NLP that means a representation of words for text analysis, typically in the form of a real value vector that encodes the meaning of the word, such that the words that are closer in the vector space are expected to be similar in meaning. Word embedding can be obtained using a set of language modeling and feature learning techniques where words and phrases from the vocabulary are mapped to vectors of real numbers. Conceptually, it involves the mathematical embedding from space with many dimensions per word to a continuous vector space with a much lower dimension. Methods to generate this mapping, including neural networks, dimensionality reduction on the word co-occurrence matrix, probabilistic models, explainable knowledge-based method, and explicit representation in terms of the context in which words appear. Word and phrase embedding, when used as the underlying input representation, have been shown to boost the performance in NLP tasks such as syntactic parsing and sentiment analysis. So, in simple language, word embedding are vector representation of a particular word. Having said that, what follows is how do we generate them? More importantly, how do they capture the context? Word-to-vec is one of the most popular techniques to learn word embedding using shadow neural networks. It was developed by Google in 2013. Word-to-vec is a word embedding technique for solving advanced NLP problems. It can iterate over a large corpus of text to learn the associations or dependencies among words. After we talk about the concept of word embedding, let's discuss the motivation behind it. Consider the following similar sentences. Have a good day and have a great day. They hardly have any different meaning. If we construct an exhaustive vocabularies, the vocabulary would be a curly bracket, and inside the curly bracket, there are 5 unique words. Have, a, good, great, and day. Now, let us create a one-hot encoding vector for each of these words in the vocabulary. The length of our one-hot encoding vector would be equal to the size of vocabulary, which is 5. We would have a vector of zeros, except for the element at the index representing the corresponding word in the vocabulary. That particular element would be 1. The encoding below would explain this better. You can see that each individual word will have a unique vector to represent them. If we try to visualize these encodings, we can think of a 5-dimensional space where each word occupies one of the dimensions and has nothing to do with the rest. This means good and great are as different as day and have, which is not true. Our objective is to have words with similar context occupy close spatial positions. Mathematically, the cosine similarity between vectors should be close to 1. Here comes the idea of generating distributed representations. Intuitively, we introduce some dependence of one word on the other words. The words in context of this word would get a greater share of this dependence. In one-hot encoding representations, all the words are independent to each other, as mentioned earlier.